Supervised machine learning requires labeled training data. And we, as researchers in this field, too often assume this data to be given, to be a fixed asset that cannot and does not need to be changed. But for many real applications, data acquisition is the crux, the most difficult aspect of putting machine learning into practice. So, how do you acquire labeled data? In active class selection, we assume a class-conditional data generator that's capable of producing feature vectors for arbitrarily chosen classes. For example, an experiment, a simulation, or a search engine. Having access to such a generator, we can try to optimize the proportions of classes in our training set. In fact, we must decide for some class proportions before any data can be generated. To this end, existing strategies for active class selection follow either of two approaches. First, the most straightforward decision would be to generate the training data with those class proportions that need to be handled later, during deployment. However, you do not always know the deployment class proportions precisely, which renders this approach unfeasible in many situations. A second approach is therefore to choose the training class proportions iteratively, based on the performance of some preliminary classifier. In spirit, the idea of performance evaluation, acquisition choice, and retraining is similar to active learning, but assumes a class-conditional data generator instead of an oracle. Unfortunately, the existing performance-based strategies completely ignore the deployment class proportions and therefore introduce label shift. This means that the training class proportions do not match the deployment class proportions and therefore degrade the performance of the resulting classifier. But isn't there anything between the two extremes of precise knowledge and full ignorance of the deployment class proportions? Our proposal is a new data acquisition strategy that incorporates prior beliefs about the class proportions that are handled during deployment. These prior beliefs can express arbitrary degrees of uncertainty, from total ignorance to precise knowledge. Domain experts can specify their personal beliefs through a suitable prior distribution, which is then reflected in the class-conditional acquisition of the training data. Long story short, we compute a theoretically justified upper bound of the classifier's loss, which we then marginalize over the prior. The goal is to minimize the marginal in order to choose the training class proportions that perform well in all likely deployment scenarios. We approach this minimization with a gradient step that we take in each iteration of the data acquisition loop. Experiments suggest that this proposal indeed works well in practice. The foundation of our active class selection strategy is the upper bound of the loss, which is part of a theory we are presenting at the research track of ECMLPKDD this year. If you are interested in the details of our strategy and our theory, you can always take a look at the two papers and at the video presentation of the other track. Also, feel free to reach out at any time. So far, thanks for watching.